important thing to understand about the K value. We skipped it, it's in E. Let's turn to 4A3, part E. Kate, read it for me.
For first order reactions, half-life is often used as a representation for the rate constant because they are inversely proportional and the half-life is independent of concentration. For example, radioactive decay processes provide real-world context.
Okay, so there's this concept called a half-life. What's a half-life?
The time it takes for the thing to
The time it takes for half of something to undergo its change. Well, that amount of time, half-life is really the amount of time, depends on the order of reaction. If the reaction is zeroth order, love that word, zero. Then if we look at what it would take to go from, say, 1 molar to 0.5 molar to 0.25 molar to 0.125 molar, well, the first half-life occurs right here. We sometimes use the abbreviation T1 half.
Then you get T2.
For the next half-life, right here. That's the second half-life. The third half-life, to cut in half again, is right here. So what's happening to the half-life?
It's halving.
It's getting shorter. Not necessarily halving, it would depend on the slope.
Well, you said zeroth order,
Wait, what is that?
But would it
Is that
depend on the
plus
slope?
but it's still happening.
Yeah, you're right.
What's that thing on x-axis?
Because the slope's coming.
Half-life.
If the slope's not 1,
Wait.
then a change of 50% here isn't going to be a change of 50% here.
No, but it's half each time. Because it's half that way.
This is halving.
Yeah, exactly.
The
But if it's
concentration is halving. The times are not necessarily.
But in this case, because it's constant,
I suppose whatever this length is,
it's half the
it's got to be proportional.
Is
Wins!
that T or plus?
T. T1 half. The half. Okay? This is zeroth order. First order, if I graph concentration versus time. Now I don't want to confuse you because remember the test for first order, what do we graph?
just concentration.
For first order, natural law.
Natural log.
Oh, no,
To
the
test
first
whether
order,
it's
yeah.
first order, we got to graph the natural log, and that should be a straight line. But if we're graphing just concentration versus time, we're going to get some curvature, right?
Yes, sir.
Now, if we look at the half-lives here, first half-life is here when we cut our concentration in half. Second half-life is here when we cut it in half again. Third half-life is here when we cut it in half again. What do you notice?
Same.
The half-life for a first-order reaction is always constant. It takes the same amount of time in a first-order reaction always to cut the concentration in half. In zeroth order, it doesn't, because in zeroth order, because the rate is constant, it takes less time if we have less stuff. But in a first-order reaction, it actually takes the same amount of time, no matter how much we start with, to cut that amount in half. So, because that has a constant value, there's a relationship between the length of this half-life and the rate constant. And it's the last equation under kinetics of your equation sheet. What does it say?
T1 half equals 0.693 over 10.
So if we know the rate constant, we can take 0.693 divided by the rate constant, and it will tell us the half-life.
Wait, what was 0.693 again? Just natural one or something? For E or something?
Well, how do we get this number, this 0.693?
And that's something to do too.
If we use the first order integrated rate law, which says the natural log at some time minus the initial natural log of the concentration equals negative KT. Well, we're saying, let's start with some concentration. Maybe we start with 1 molar. Right? After 1 half-life, what should the concentration be? 0.5 molar. What's the natural log of 0.5?
That's what it is. Yeah. It is.
Nobody has a calculator, but yeah.
Oh my god, it's like negative.
Negative.
Negative
Oh
0.693.
yeah, it says less than
Right? Natural log of 1?
0.
0, right? Because what do you raise e to get 1? 0, right? So negative 0.693 minus 0 is negative 0.693 equal to KT. Now we can call this T T1 half because we're talking about the amount of time where we cut the concentration in half. The negatives will cancel, so I get 0.693, and then I divide by K. All right? Now that's special. It's on your equation sheet, first of all, because there are lots of first order reactions, including all nuclear reactions. All nuclear reactions obey first order kinetics. But also because it's the only order of reaction where you get a constant half-life. All the other ones, it depends on how much stuff you have, so the half-life changes. In 0th order, it changes. If we look at second order, in second order what happens is actually that the half-life increases over time.
That's second order?
Yeah. Well, I always have a really hard time drawing second order.
Let's
But
show you
in a
steeper curve.
But yeah, in second order, the first cutting in half is really quick. The second cutting in half is much longer. Third cutting in half, longer still. Okay, so 0th order and second order, the half-life is not constant, so there's no equation you can use. You'd have to use the integrated rate law, plug in your concentration, plug in your new concentration, or half of it, right? Half of the concentration for which you're trying to calculate the half-life, plug in your K value and solve for T. That would be the only way to find the half-life for 0th order or second. Okay? So I wanted to point that out because it's in 4A3 part E, and then they actually even say in Learning Objective 4.3, the student is able to connect the half-life of a reaction to the rate constant of a first order reaction and justify the use of this relation in terms of the reaction being a first order reaction. I don't know, I just read that, but it didn't make any sense. Basically, they want you to be able to calculate the half-life. So if you go through like the problem we did the other day where we went through and we actually found K, you should be able to then calculate the half-life. For that reaction, I think we had 10 to the minus 17th was our K value. So if we're taking 0.693 over 10 to the minus 17th, it's going to be a whole bunch of milliseconds, some very large number of milliseconds, right? If we took our K from yesterday, that we got 1.7 times 10 to the minus 1.8 times 10 to the minus 17th, there we go. Right? Then we're going to get a really big half-life.
Have they gone asked us besides first order?
No, they won't, because that's the only one that's really useful to actually talk about a half-life. The other ones, you just want to use the K value. All right, but they also say that you can justify this relation in terms of the reaction being first order. So they might ask you something about why can we come up with this relationship for first order reactions. It's because the half-life is always constant. It always takes the same amount of time to cut the concentration in half. That's not true for 0th or second. All right? Cool. Quimai, you want to stop the video for me? So tomorrow, we'll get into